Welcome to Frontline Systems special webinar on the art of designing models to get the best answers using the power of Analytic Solver. This webinar is an outreach from our dedicated customer success and support teams to make sure you're getting the most out of our products. And this is the first in this series. Here is the plan for today's webinar. We will focus on mathematical optimization using Analytic Solver, desktop and cloud, and we will talk about what may make it difficult to get the solutions that we expect. So we are going to start with an overview of different solving methods. Our goal is to emphasize how the choice of each formula for your objective and constraints are essential in determining the resulting structure and therefore solving method, quality of your solution, and the performance. With this in mind, we look at modeling from a different perspective and apply a linear approach whenever it is possible, whenever it might not seem to be your first choice. And we will learn it can facilitate getting better answers. As time allows, I will share how to avoid common modeling mistakes in order to make smooth path for you towards successful achievement of solving your business problems most efficiently. Let's review some concepts to make sure everybody's in the same page. We all know in order for solver to get the best to help you make the best decision for your business problem, you need to define your business problem in solver modeling language. You have input data from your business. You have to come up with formulas and use these formulas to describe key aspects of your business work and the different components of optimization model. You have decision variables, you have constraints, and you also have a goal that you want to optimize, minimize cost, maximize profit, and much more. If you have objective and no constraints, solver will perform unconstrained optimization problem, okay, and seeking the largest or smallest possible value for objective cell. So here you have just only decision variables and an objective, okay. If you want to maximize or minimize an objective subject to constraints, then you have a constraint optimization. In this case, mathematical methods needed to solve this optimization problem depend on relationships defined by your formulas between your objective, constraints, and input, which are the variable cells, or decision variable cells, okay? So when you hit solve, Analytic Solver tries to find an optimal solution for your problem and achieve the goal that you have requested it, right? To maximize or minimize the objective for you, okay? So there are three main solving methods. We have simplex LP. This method solves linear programming or constraint linear optimization problems where all the formula relationships are linear, and it uses the simplex method. Then we have GRG nonlinear. It solves nonlinear programming or constraint nonlinear optimization problems when formulas are smooth linear or nonlinear using generalized reduced gradient method. And then we have evolutionary method when there are no restrictions on formulas, and it uses genetic algorithm and other evolutionary methods, okay? If you have integer variables, binary decision variables, mixed integer programming methods are also available to you. These three solving methods make different assumptions about how your model behaves. These assumptions allow solver to be selective about which decision variables to change and by how much enable it to find solutions much faster. If you're using simplex method, it already assumes that formulas that calculate your constraints on objective are all linear functions of decision variables. And then if that's true, this solver can quickly find globally optimal, meaning the best guaranteed optimal solution for you, feasible solution for you. If you are using GRG nonlinear, it assumes that formulas that calculate objective and constraints are smooth linear or nonlinear, okay, functions of decision variable. And when it's true, it will take more time, it will do some more work, but it normally finds a locally optimal solution, best feasible solution in the region around the starting point. Now, imagine you're working with evolutionary method. It makes no assumption about the formulas that calculate your objective and constraints as functions of decision variable. So solver with the evolutionary method takes much more time, and it can only find a good solution, improves it from the starting point, but it's not an optimal solution. And at the end of webinar today, we'll talk more about evolutionary method, what to do, okay, how to avoid it, and then if you have it, what to do. Now you should have an idea why sometimes we may not get the solution that we want. If you're using LP simplex, the starting values of decision variables doesn't matter. As your model is linear, this method will find global optimal solution. But for GRG nonlinear and evolutionary methods, the starting value of decision variables matter. So we will talk about the multi-start option. The good news is Analytic Solver will do the algebra for you and determine the model structure, and I will show you in the next example. So, and it automatically can choose the best solving method or engine for you from dozen of choices. The main take-home message for this part of the webinar: having convex constraints is the key to find feasible solutions, and having convex objective is key to find a globally optimal solution. And all linear functions are convex. Therefore, the choice of each formula for your objective and constraints are critical in determining the resulting structure of your optimization problem type and the solving method that can be used, okay? And this is where spending more time, investing more time can reward you significantly down the road with better quality of solution and performance. Any questions so far? Dan, did you want to add anything here?
Well, a little later, perhaps we could try to give people some insight into why these things are true. You know, this is all a matter of the process of searching. Optimization is a search through a multidimensional space, and when and you know, you're bounded by constraints. You got to search within the feasible region bounded by the constraints. And when the constraints are linear, when all the constraints are linear, you naturally have like it's almost like a closed box, which is a convex region. And when the objective is also convex, then you can proceed quite rapidly and for sure to the optimal solution, globally optimal solution. And in the case of nonlinear, non-convex models and so on, it gets harder. And that's really the heart of why GRG method takes more time. The evolutionary method takes far more time. That's about as much as I should try to say right now, though. Thanks.
I have chosen this refinery operation model for our first example. So this is one of the shipping examples. I remember for shipping examples, just go to Analytic Solver help, and then you just go to example models, and under optimization, you have all different kinds of example, different industries, and including this refinery operations model. So just in summary, a refinery purchases 2 crude oils, crude 1 and crude 2, and these oils are put through 4 processes: distillation, reforming, cracking, and blending, to produce petrols and fuels, which are then sold. And then the question is, how should the operations of refinery be planned to maximize total profit? Distillation separates each crude oil into different fractions according to their boiling points. So you can see this picture here, that there's a furnace, and then the distillation separates them according to boiling points. The fractions into which 1 barrel of each type of crude splits are given in the first table. Okay, so these are the inputs to the problem. Then we have reforming, that produces a product known as reform gasoline, and they're all about the different octane numbers. And then we also have cracking, that is used to maximize the use of oil. So these are different steps of the cracking process, and then this is the blending process. The blending, which is the last step in the model, is the process of mixing different refinery products to make finished petroleum fuels, and we create grades of gasoline that you can see at the pump, okay? And the objective here is to maximize profit, and profit, the contribution to the profit are from premium petrol, so regular petrol, jet fuel, fuel oil, and lube oil, okay? And when we have an optimization model, what can we do to understand more about this model? Analyze the structure and then decide which engine to use. Okay. For this, you can use this button, Analyze Model Structure, without solving it. Okay, so let's click on that. Let's see what kind of model we have. It's a guided mode. It's helping us understand. This model is linear programming convex. Okay, let's click on next step. And you always get an output report. So I was doing some tests, so this is just telling us the structure of this optimization model. You can choose the engine you want, or you can let Analytic Solver choose the engine for you. So you always have the option to automatically select engine and let Analytic Solver choose the engine for you, because it has the capability to analyze the formula and choose the best engine for you. And I have all the engines installed, so the standard engines and also some plug-in additional engines. So let's just use LP quadratic engine and solve this optimization problem. You can just click on optimize or that green arrow. So I'm going to use, I think this go to webinar is kind of blocking me here. Okay, so let's click on, so let's erase all of this and click on optimize. Same way, we're going to guided mode. This is the LP convex model. Next step, it solves the model, found the solution, all constraints and optimality conditions are satisfied. So remember what we talked about. If all the formulas are convex, it's very easy. Analytic Solver quickly use simplex LP method, and here are the results, okay? Total profit for operations of this refinery, which is couple of some product functions for the products that we talked. Anytime you get this solver result message, it's a hyperlink, so click on that. It actually brings Analytic Solver help and gives you some information. Now let's look at the result. We have mainly premium petrol, and there's no constraint really on regular petrol. So now I'm going to create some scenarios for you. Okay. Imagine you have to ensure that you have to produce regular petrol, and it should be the minimum production of 20% of the total petrol produced. Let's add this constraint together. We have to calculate the total regular petrol, which is cell D36, divided by total petrol produced, which is D36 plus E36, right? Are you following me? It's a formula bar. So I have this formula, okay? And I want to make sure this is greater than, say, 0.5%. This is a constant number. So let's add this constraint. So just go to constraint. H39 should be greater than the right-hand side, 0.05. Let's click on solve. Let's click on continue. Immediately, you will notice that this model is no longer linear programming convex. It's actually a nonlinear programming non-convex model. Just adding a simple constraint, the ratio of petrol produced. And we want to ensure that we are producing some regular petrol. Now it says the choice of standard LP quadratic is no longer accepted, as you can see down here. Analytic Solver is analyzing the formulas and making sure we're choosing the correct engine, right? Nitro engine is one of the engines. You can also use larger scale GRG solver and then click on next step. Nitro solver get the result for us and ensures that you have to get the regular petrol 5% of between the regular and premium. But we saw that adding the one constraint, it changed the structure of this optimization model. Now, let's see how we can think about this in a different way. You could choose a different approach, and with some reformulation, we can keep the model linear. So this is the formula that we actually used, right? D36 divided by D36 to E36. So let's go back to our slides, and I want to show you the ratio constraints. Ratio constraints come in different ways. Could be two variables divided by each other, x1 divided by x2. It could be a percentage constraint like what we had. It could be a weighted average. These very easily can be transformed to a linear format. Multiply both sides by the denominator and collect the terms and do the math according to signs, and you will have easily a linear function. This is where you start and this is where you end. So let's go back and use the same approach for our model. So we have D36, D36, okay, and then it should be greater than or equal to 0.5 times D36 E36, okay? So that's the right hand side, and then we have equal 0.05 star the sum, right, which is a sum of these two, right, D36 and E36. So now when you move everything to one side, it would be D36 minus this part, the denominator times 0.05 greater than 0. Okay. This minus, and click enter, and then now we can add this as a constraint. This should be greater than or equal to 0. So let's go back to the model tab. Let's remove the nonlinear version of the constraint, which is in H39. I'm going to remove that. So to remove, you can just uncheck the constraint, or you can actually just delete it. And now we want to make sure this constraint, did I add it? 42. Yeah, so we have the new constraint added. H42 greater than or equal to 0. So now let's analyze the structure. Continue. Model is LP convex. With a simple math, we saved ourselves the hassle of working with a nonlinear model. Next step. Okay, now next, let's solve the problem. And we get the optimal solution, okay? This was just one example that how with a little more work, you can get a better result, okay? So now let's talk about other conditions. There are a lot of conditions that you can use integer variables to help you for linearizing other conditions. One of them, for example, is when you have an if function. So let's go back to our example. I want to show you another condition. The coefficient for producing regular petrol was 600 per barrel, and for the premium it's 700. Okay, now imagine this situation. Refinery have to give a discount if they are not producing enough regular petrol as per the contract. So we have this condition that if the amount of produced regular petrol is less than 500, they have to give a huge discount to the user. So instead of 700 per barrel, their profit actually is reduced to 300 per barrel because they have to purchase it from another refinery for the regular petrol. Regular profit petrol and then premium petrol will be dropping to 300. If D36, which is amount of petrol produced for regular petrol, is less than 500, and if it's true, the profit for premium is 300, and the profit otherwise, if you're producing enough regular petrol, the profit remains on 700. I calculated the new objective function, including this if function. So let me show you. So I have the if function in this cell. Okay, and then I incorporated in the objective function. So now let's add this, replace it with our current objective. So let's change this. Instead of C42, we're gonna use G56, okay? And then let's click on solve. Continue. Now look at this. Your model is a non-smooth model, no longer linear LP because of adding that if function to the model. And let's click on next step. And look at this, we are using a standard evolutionary now to solve this optimization problem. Look at this timing already. That model was solved like just a few seconds. Now it's taking time to set up the model, and you can see the engine selection is evolutionary. And this one relatively solves fast. Is not one of the worst ones. It's a pretty small example, but still you can see and appreciate how adding an if function changes the structure. Now we are using the evolutionary method to look for a solution. So let's give it a few seconds. Okay, so it says solver cannot improve the current solution and all the constraints are satisfied. So look at the difference in the message. No longer someone found the guaranteed optimal solution. It just says solver cannot improve the current solution. So we found a feasible solution, and evolutionary method, after searching and searching, figured out that it cannot improve the solution anymore, so it will stop. Okay. Later we will talk about that evolutionary engine doesn't have a stopping criteria and just uses some heuristic methods, heuristic conditions, or some of the condition you have to give it so that it stops, for example, after 1 hour, after 30 minutes of searching and everything. Okay, but this one was a very small model, relatively small example, and you can see still it took much longer. So let's click OK, and we get the result. Now let's talk about using a different approach. Not always you can make everything linear, but this non-smooth function can be changed to a linear function, but because it is used in objective function, it's multiplied by decision variable, at the end it will be a quadratic function. Okay, so let's go back to slides. So I will show you it can be done in this situation. Okay, so how can we avoid if functions? We can use integer variables, and integer variables such as discrete quantities, right? But binary variables such as when you have yes no decisions, your variable only takes 0 and 1, and binary variables can help us to exactly avoid some of the if or non-smooth functions. Okay, situations. There are other conditions that binary variables can be used. Okay, if you want to impose some extra condition, and you want to make sure you enforce a condition or use them for threshold levels. Binary variables can be used for some of these conditions. Okay, if, nested if, either or constraint, absolute value, minimum, maximum. Now let's look how do we linearize this kind of if function. You need to add two constraints. If this condition is true, you have to use this function. If not, you have to use this function, right? In our case was like it was 300 and 700, right? So we want to include a new integer binary variable. So this variable only takes 0 and 1. Here we call it like some new variable in cell H5, and it is 1 if conditional argument is true and it is 0 otherwise. If the condition argument is true, so it is taking 1, and J5 is greater than 500, right? That's the main part. My handwriting is not that great. So if J5 is greater than 500, this new variable takes 1, and if it is less than 500, we have to make sure this variable takes 0. And then we replace the if with this formula. So imagine J5 is 500 above, like 600. So this new variable is taking 1. So let's put 1 here. So L5, the condition when it is true, times the new variable, which is 1. That's exactly what we want. If J5 is greater than 500, we have a 1 for H5. So let's replace 1. What do we get? We get L5. Now, the condition is false. J5 is less than 500, so we get 0 here. So this part becomes 0 plus H5 is 0, so we get M5 times 1, we get M5. So I'm showing you the math here. If true, L5. If false, we want M5, okay? So the replacements are demonstrated here, that how this new variable, if it takes 1 or 0, what would be the resulting formula? Okay, how we get L5 and N5. So replacement function is pretty easy to understand, right? Now you have to do a little bit more math, okay? If J5 is greater than 500, J5 greater than 500, move everything, okay, to one side. So J5 minus 500 greater than 0, okay? So this is a positive value. It's greater than 0. And you pick a very large number, which is bigger than any possible value for that decision variable here, J5. So we call it big M, okay? You might have heard about that. You have to add these constraints, okay? And then in the false condition, which is J5 less than 500, you'll move everything to one side, M times 1 minus H, okay? And this would be your upper bound, okay? And you add these two constraints. So let's go and practice this in our optimization model. So I did all the calculations. I put 30,000 for my big M. You can put higher, okay? So this is this cell. Let me highlight for you. This cell is my new binary variable. So let's make sure I've added this to the model. K58, okay? So this is our new binary variable. Let's verify. This is K58, new binary. Do you know how to add it? So let me just quickly show you. Let me delete this and do it together. So select empty cell, go to Analytic Solver, decision, normal. So first define the cell as a decision variable, then go to constraints, variable type or bound, and define it as a binary decision variable. It as a binary restriction. So as soon as you do that, you will see exactly same way. K58, it's binary and it's a new variable. So that's like that H5 in the calculation. Okay, so instead of H5, I have K58. Now I do all the calculation, 500 minus D36, and then this is where the breakpoint is happening, right? D36 less than 500, and then how the profit function changes, okay? So 500 less than D5 minus D36, and then I also have D36 minus 500, and then I have the right-hand side values, which are big M times the new variable, and big M times 1 minus the new variable. Okay, so now let's add these constraints. So this is G59, and I have them, so I just have to check them, okay? Here, G59 should be less than K59. Let's check this. And then G60 less than K60, okay? Those are the two constraints you have to add. And then how do we calculate the if function replacement? So it's the 500 times the new variable plus 700 times 1 minus the new variable. Then I went ahead and replaced all of that in the objective function calculation. This is not going to be a linear function, but it's going to be a quadratic function, which is much better than having a non-smooth operation. So I just wanted to show you a condition in that not everything is going to be linear. Having a quadratic is better than having a non-smooth operation. So now we have to point to this new objective function. G56. Instead of that, let's use this new objective function in cell H64. Let's go ahead and analyze the model. Now let's look at the structure. Continue. You can see that the model now is diagnosed as quadratic programming, okay? QCP. And it's not evolutionary. Our choice is not recommended anymore. For example, you can use a GRG or largest scale SQP solver to solve it next step. So let's change the engine and let's go ahead and try to solve this model. Continue, go ahead, and solver found solution, and actually optimality conditions are satisfied, so we got an optimal solution for this optimization. So from a non-smooth model to QCP or quadratic problem, and we got the solution that is optimal. I have this if function. We also have some descriptions in our user guides. This is like a more general formula that you're dealing with situations that you have a function of decision variables, and then if the condition is true, and the main thing is in this if function is that this first argument depends on your decision variable, okay? So there is a jump that is happening, and the value of petrol, you remember that our situation jumps from 300 to 700. Okay? And that is what makes the model non-smooth. It's no longer like a smooth change. It just jumps from one value to another. And our goal is to eliminate the non-smooth behavior. What if you have to minimize maximum of 2 decision variables and you just add these constraints and introduce a new variable that's equivalent to maximum of 2 variable, and that is how you enforce this variable is greater than each of the variables. Okay, so these are all linear approaches, and these slides are available for you. If you have any of these situations, you can use a linear approach instead of the non-smooth approach, because min, max, these are Excel functions, and these are non-smooth, and they change the structure of your optimization problem. Then you're forced to use a different kind of engine, evolutionary engine, and it may cost you in terms of getting a guaranteed or better optimal solution, okay, rather than just getting a feasible answer, okay, feasible solution. Absolute value, this is another one that happens a lot. We have seen it with our customers that can make the model using Excel formula. Absolute value is going to make the model non-smooth, and you can easily linearize absolute value functions. Dan, did you want to add anything at this point?
No immediate comments. I am answering questions. Let me go ahead and try to answer this one audibly. So Eric asked, how's using a binary constraint different from just defining a constraint where the variable equals 1 or 0, in your model? And presumably there's something else in the model that forces that variable to be either 1 or 0. Basically, the difference is by defining the binary constraint as part of the solver model, you're telling the solver, the search algorithm, okay, at the solution, this variable is going to be either 1 or 0, so you only have to search in space in the places where this variable is 0 or it's 1, and you can skip all the intermediate values. But if it's just implicit in the formulas, that the the solver doesn't know that, and so it does have to search all the intermediate values, and at the end it will find out that, okay, the solution's at 0 or at 1, but it had to do all that extra work. So the whole idea of adding integer variables and binary variables is to structure the search that the solver is going to have to perform, and that makes a huge difference in the difficulty of the problem. Okay, let me just leave it at that right now. Also, I will have to leave for a doctor's appointment in about 10 minutes sharp, 9:59 Pacific time. So if we run over, I'm sorry, I won't be able to answer questions after that. Got to get to a doctor's appointment.
Thank you, Dan. As Dan mentioned, there are other ways to help to have a better structure. And one of them is, for example, efficiently add integer variables. Another one is to add non-negativity when you're sure your decision variables are taking positive values. And it's really simple, for example, for adding non-negativity constraint to the model. So I'm just going to show you, because this is such a common occurrence. Let's go to Engine tab. For example, this is a GRG nonlinear engine selection. So there is an option for assume non-negative. And when it is true, it automatically adds the constraint that decision variables should take positive values, 0 or positive values. Okay, so this is a very quick way to help make things faster. And another way for you, if you go to platform tab, some of the engines, for example, they require a lower and upper bound for decision variables. So let's see, default bounds. So you also have these options that you can set for your models, default bounds for decisions, variable lower and upper bounds, and that also helps to the solver engines to find this answer faster for you, solution faster. Another thing that's important is to pay attention to solver result messages. So the output message sometimes is red, and it is very helpful if you pay attention to these result messages and read what it's telling you to get the result. For example, in one scenario, you might get solver converge to current solution, and it says that it doesn't say optimality conditions are satisfied. So basically, then you have to pay attention to the convergence option and use a different starting point. Okay, so pay attention to these messages. For example, it can say, hey, solver that limit or number of max time reached. So that means you have to have set these options, okay, and you have to make sure you're paying attention. So this is the conversion options. Many of solver unexpected result messages are due to a poorly scaled model. What do we mean with this? Let's go to this example. This is a financial optimization example. We have portfolio optimization. We have expected return, for example, 7%, 8%, okay, and then we also have the covariance variance matrix, okay, with these values. Now imagine another condition. I mean, this is not very accurate, but imagine the expected return was in millions, okay, and then you have these percentages or the covariance matrix, which was all like 0.07 or 0.007, okay. So usually, especially in it's a classic situation when we have financial models, we have dollar amounts in millions and billions, and the risk measure is fraction of percent. So because of the finite procedure computer arithmetic, when the values of very different magnitude are added, subtracted, or compared, the result will be only accurate to a few significant digits. And after many of these calculations, your model may suffer from numerical instability. And this happens a lot. For example, in a large complex optimization model, you get the message like solver could not find a feasible solution, or solver could not improve the current solution, or linearity conditions are not satisfied. Then you will end up with results that are suboptimal, or you may not even get what you want. What do we do in this condition? One is to avoid it. For example, don't use, like, when you see you have percentages and very small values, you could just basically try to use different units for example, for your return, okay? There's an option for automatic scaling with the engines, okay? That's one option you can use. Another way is which I like, is to get an LP report, okay, from your model and look at what the mathematical structure of your optimization model. So I'm going to compare the LP report for these two models and actually show you how you can generate an LP report and review it. So let's go to tools. Okay, so we have this optimization model, the first one with this expected returns that are in percentage. Okay, let's go tools, load save model. You change the format to output file, okay, and then you can see the output. It will save it as an LP file. Okay, I will show you again, don't worry, one more time. So this is the financial model webinar. This is the first. Let's open the model, financial model webinar. Okay, so look at the mathematical optimization in an LP format. Okay, you can see the objective, all the coefficients, all the constraints, okay, and the bounds on your decision variables. This is the LP format. Now let's look at this one. Go to tools, load save model, output file. Let's do financial webinar 2. And let's go to financial webinar 2 and look at the calculations here. E to the power of 0.7, and look at these constraints. Okay, so we are starting to see how these coefficients are different from this constraint versus this one. Okay, so LP report is one way for you to see what your structure look like. Dan, did you want to add anything regarding scaling?
I don't think so.
If you have integer constraints, sometimes you might have noticed that solver claims it found the optimal solution, but when you manually calculate, you can find ever better solution. this is a tolerance option in the task pane engine tab. Okay? So if, or sometimes you might get the message solver found the integer solution within the tolerance. Okay, in a large scale mixed integer programming, you might get these messages, but there's a default setting for the tolerance. So let me show you where that option is. Let's go to engine tab, and here, for example, I changed the integer tolerance to 0, but you have to check depending on the problem you're solving and make sure this integer tolerance is what you want it to be, okay? So you can adjust it and then start from the solution and try to find a better solution. So what if you have a non-convex problem? If you have a non-convex problem, it's really good idea to run solver starting from different set of initial values for decision variables. For GRG nonlinear, for example, there is a multi-start option. So I want to make sure you are aware of that. You can set that to true, and then it starts from different values. Start from different starting points, and then gets a better solution. Okay? And you will help the solver to increase the chances that you find the best possible or optimal solution. Use the multi-step option. So if you have a non-smooth situation and you cannot linearize it and you did all the effort, why you're not even getting a result? So you're getting or sometimes you get a solution from non-evolutionary engine. What can you do? So we know now that evolutionary solver can only give us a good solution in the best situation, and it actually has no way to know where to stop and determine whether a given solution is optimal. It uses some heuristic rule, or you might have to put a limit on computing time for it to stop and return that solution for you. Okay, now what can you do to improve this situation? Restart multiple times from the solution and tighten your conversions and tolerance values. Increase max time to allow it to run further. You can actually increase the population size and mutation rate. These are the settings for the methodology of search. And again, keep the resulting solution. Once you found a feasible solution, then you can switch to GRG and start from that solution. And then you can always also look at the population report and examine that. So remember, having convex constraints is key to find feasible solution, and having a convex objective key to find a global optimal solution. And all linear functions are convex. So that is the ideal, okay? I can share the slides with you. You can review the rest of them at your convenience. And we are here to answer all the questions. We trust this webinar refresh your modeling perspective and equip you with some methods to apply a linear approach or better approach whenever possible. If you have questions for upgrades and account queries, you can reach out to Allison. Any licensing question, and of course, if you have any modeling questions, you can always reach me at consulting@solver.com.